Now velocity potential function is denoted by phi. Okay, velocity potential function is defined as a scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction. Okay, so phi is a function of x, y, z. U is the minus del phi. U is equal to minus del phi del x. It is defined as a scalar function of space and time such that the negative derivative along x direction gives the velocity along x direction, that is u. Negative derivative along y direction gives the velocity along y direction, and negative derivative along z direction gives the velocity along z direction. Similarly, this is the polar coordinate. ur is the radial velocity and u theta is the tangential velocity. This is written like this. Okay, this is like this. Now the rotational component omega z is equal to the rotational component with respect to z axis, and the rotational plane is xy plane. Okay, that should be is equal to half del x del y this is the rotational component in xy plane. Okay, so it should be equal to half b is equal to minus del phi del y. So del x minus del phi del y minus del y, u is equal to minus del phi del x. So it should be equal to half minus del 2 phi del x del y. Similarly, minus del 2 phi minus and minus, it should be plus by del y del x. So it should be equal to 0. Similarly, omega x is equal to 0. If I derive the equation for omega x and omega y, that should be equal to 0. So omega x, omega y and omega z is equal to 0. So it can be concluded that if velocity potential function exists, then the flow should be irrotational. Okay, so existence of velocity potential function representing irrotational flow. Okay, now the continuity equation for steady incompressible flow for three-dimensional cases is just like del u del x plus del v del y plus del w del z is equal to, this is the continuity equation. Continuity equation for case of steady and incompressible flow. Okay, so for steady incompressible flow, the continuity equation for three dimension is just like this. Okay, now del x, u is equal to minus del phi del x plus del y, v is equal to minus del phi del y plus del z is equal to omega w is equal to minus del phi by del z is equal to 0. That is the omega z. Okay, and this is the w. Okay, this is the w. Okay, now minus del 2 phi del x2 minus del 2 phi del y2 minus del 2 phi del z2 is equal to 0 is, so del 2 phi del x2 plus del 2 phi del y2 plus del 2 phi del z2 is equal to 0. This is the Laplace equation. This is the Laplace equation. So it can be concluded that if velocity potential function satisfies the Laplace equation, it is a possible case of fluid flow. That means it's a case of steady incompressible fluid flow. So first thing is, if phi exists, then the flow should be irrotational, and if velocity potential function satisfies the Laplace equation, that should be steady incompressible fluid flow. Okay. Now stream function. What is stream function? Stream function, it is defined as a scalar function of space and time such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction. Okay. So this is the coordinate. This is the x direction and this is the y direction. So derivative of psi is with respect to x gives the velocity component right angles to that direction. So velocity, so the derivative of psi with respect to x gives the velocity along y direction, that is the v. Okay. Similarly, derivative of psi with respect to y gives the velocity of z direction, a velocity of this direction, in this direction. So it should be minus u at this direction, that should be, it should be minus u. So del psi del y is equal to minus u. Similarly, this is the polar component. Okay. Now for the case of two-dimensional continuity equation for two-dimensional flow is del u del x plus del v del y is equal to 0. In place of u, you written as minus del phi del y. Okay. In place of u, you can write as minus del psi del y. Okay. And in place of v, you can write as del psi del x. So this is the minus and this minus, it should be equal to 0. So it can be concluded that if stream function exists, then it's a possible case of fluid flow, that is the steady and incompressible fluid flow. This is the continuity equation for steady and incompressible fluid flow for two-dimensional cases. Okay. So the existence of psi, that is the existence of stream function, indicating the possible case of fluid flow, that is the steady and incompressible fluid flow. Okay. Now, but it may be irrotational, or rotational. Okay. Now the velocity rotational component in xy plane or with respect to z axis, that is the omega z is equal to half del v del x minus del u del y. In place of v, you can write, it can be written that del psi del x, and in place of u, you can write as minus del psi del y. Okay. So that should be equal to like this. Next, if omega, this rotational component, is 0, then this equation should be equal to 0. Okay. And this equation is called the Laplace equation. This equation is called the Laplace equation. So it can be concluded that if stream function satisfies the Laplace equation, it is a possible case of irrotational flow. So it is the difference between the scalar function and stream function. Now the topic is equipotential line. What is equipotential line? Equipotential line is a line along which the velocity potential function, that is phi, is constant. So phi is equal to constant, so d phi is equal to 0, and phi is a function of x and y, so you can read as d phi is equal to del phi del x into dx plus del phi del y into dy. Del phi del x, that is equal to minus u, del phi del x is equal to minus u, del phi del x is equal to minus u. Okay. And del phi del y is equal to minus b, del phi del y is equal to minus b. Okay, so this is the final equation. Now if d phi is equal to 0, then this quantity should be is equal to 0, and dy dx should be is equal to minus u by v. Dy dx is the slope of the equipotential line, so slope of the equipotential line is equal to minus u by v. Okay, and the line of constant in stream function, this is the line along which the stream function is constant, that is the psi is equal to constant, so d psi is equal to 0, and psi is a function of x and y, so d psi is equal to del psi del x into dx and plus del psi del y into di. Now del psi del x is equal to del psi del x is equal to v, so in place of del psi del x you can it can be written that v dx, and in place of d psi dy minus u, that is d psi dy is equal to minus u, so it can be written as minus u into dy. Okay, so for the constant line of constant in stream function d psi is equal to 0, then this quantity should be is equal to 0. Okay, so dy dx is equal to v by u, that is the slope of the line of the constant stream function. Okay, so this is the slope of streamline constant. The line along the streamline is the line along which the stream function is constant. Okay, now the product of streamline and equipotential line should be equal to minus 1, because the slope of equipotential line was minus u by v, and slope of streamline is equal to v by u. The product of these two slope should be equal to minus 1, so it should be concluded these two lines, that is the equipotential line and streamlines, are orthogonal to each other. Okay, now this is another relation between stream function and velocity potential function. U is equal to minus d phi dx, and that is equal to also minus d psi di, so it can written as d phi dx is del phi del x is equal to del psi del y. Similarly, v is equal to minus del psi del y, and b is equal to del phi del x, so del phi del x del phi del y is equal to minus del psi del x. Okay, thank you.